शान्तं मारकोटिं प्रकाशं शान्तं महाकाव्यनाटकादिप्रियम् महाकाव्यनाटकादिप्रियं मूषिकवाहन मोदकप्रियं महागणपतिम्.
Thank you so much, Shiva. Now, I request Dr. Anisha Balasubramanian, Madam, Assistant Professor, Science and Humanities, to introduce our chief guest. Please, Madam.
Thank you, sir. It's with great pleasure and immense pride that I would like to introduce our speaker for today, Dr. Mohan Venkatramana. He is a serial entrepreneur and the founder president of Syntronics Inc., a technology research and development and business strategy solutions company specializing in developing end-scale concepts to marketable products and dedicated to incubating several R&D ventures in collaboration with other entrepreneurs. He has extensive experience building solutions and companies for niche areas in multiple verticals that include life sciences and healthcare, clean energy, retail services, telecommunications, software, and enterprise solutions, AI, ML, big data, cloud computing, and mobile solutions, to name a few. His focus is on identifying the current and future trends in emerging areas of technology and creating new technologies to help bridge the gap to the future. He has a very impressive academic record of having studied in uh, institutes of repute in India and abroad. He received his BTech degree in chemical engineering from IIT Madras, his MS in energy engineering from University of Illinois Chicago, and his PhD in chemical engineering from MIT. He's worked at AT&T Bell Labs for 10 years as a systems engineer, where he worked on various telecommunications projects and designing nationwide network services. Recently, he's launched a non-profit enterprise called Expertise to help students to pursue their career interests in scientific research and has taught advanced bioinformatics, artificial intelligence, data science, and advanced computing to many batches of students. Along the way, he's worked briefly at Microsoft, Amazon, Fred Hutchinson Cancer Research Institute, Inoscope, Cigna Healthcare, Caltech, and Global Classroom on various projects. Currently, he's involved in launching large-scale joint ventures in biosciences, energy, and semiconductor fabrication ventures, including building a semiconductor fabrication facility by bringing together microelectronics experts in USA and India and help make India a world-class manufacturing center in semiconductors and help make the Make in India initiative a success. He is also a leading initiative to support building EV batteries and launching several startup joint ventures in India with foreign collaborations and partnerships under the branding of Expertise Incubator. He is passionate about entrepreneurship and would like to mentor students who are interested in launching startup ventures. With many years of entrepreneurship experience and mentoring several MBA students at Seattle University, Health Innovators, a nonprofit, and Cambridge Innovation Center, Dr. Mohan enjoys working with students and helping them in their career. At CIC, he organized and delivered a year-long course called Evidence-Based Entrepreneurship in Healthcare and led ideation and brainstorming sessions. He was also an educational counselor for MIT, helping guide students who are applying to MIT. He founded Expertise, a non-profit initiative to motivate and encourage students around the world to prepare for career in scientific research and development in bioinformatics, system biology, and related biosciences, as well as other STEM areas. Prior to Expertise, he had co-founded two non-profit organizations, one called India Rural Community Project Initiative for evaluating new technology introduction opportunities for rural development in energy and healthcare, and the other called Seattle Institute for Peace Studies for fostering non-violent ways of conflict resolution in young children as well as adults. Warm welcome again, sir.
Thank you. Dr. Natarajan, what am I supposed to do?
I think he's lost connectivity. So here we have having rains the past few days, so the network is horrible. Probably you can address the gathering, sir.
I'm not getting the clear voice here, but you want me to start the process, start the presentation?
If you could go ahead, sir. Hope I'm clear.
Yes, you're clear. I could hear you, but trying to understand. Little bit garbled. So let me know what I should do. Should I start or should I wait for something?
Um,
I wait your instructions. Can you hear me? That's a problem. Madam, is there anything particular? I'm not hearing you.
hello.
Yes.
Yes, sir. Hello, sir. I'm Dr. Natarajan, sir.
Yes. Go
Yes,
ahead.
sir. You may proceed, sir. We have some net connectivity issue.
Okay.
You
All
may
right.
start, sir, please.
Okay. Thank you. Appreciate it.
Okay,
Let
sir.
me
Sir,
make the
you are
present.
sharing PPT, sir?
Yes, I will present the screen first, and then eventually I'll send you the.
Yes, sir. Okay, sir.
Okay, thank you. Okay.
Yes, sir. Visible, sir.
Okay, great. Wonderful. Okay.
Yes, sir. Visible, sir.
I'm getting some feedback. Um, Somebody needs to mute the button. Okay, thank you. Good evening, good morning, everybody. My name is Dr. Mohan Venkatramana. Thank you very much, ma'am, for your kind introduction of me. My company is called Syntonix, and I'll be talking today about innovation in startups and semiconductors. And I try to parse that sentence. There is an innovation in startup which has its own context, and innovation in semiconductors which has its own context. So what we are going to talk about, and I'm going to begin with a story, a real life story, a story that many of us at the age group we are in have actually lived through the history. For the young people, however, it looks like a history. It looks like something that happened many, many years ago, even though it was time, right, happened in our lifetime. So I'm going to start talking about the past, the transistors, and a little bit of a history about how the transistors came to being at Bell Labs. And we will move quickly to the present, And I'm going to focus purely on the semiconductor processing, manufacturing semiconductors, because that has a relevance for India. And we'll talk about some of the challenges that we face in bringing the semiconductor processing. We'll be talking about the future, where we talk about innovation opportunities in semiconductors, which is probably what many of us are interested in. And we'll be talking about our focus on Atmanirbhar Bharat, our Prime Minister Modi's initiative, and why it is important and what we are doing about. And as a part of the startup, innovation in startup, I would like to explain what we are doing in Expertise Incubator as a strategic roadmap. And hopefully, this will give a context, a pathway for young students to see what they can do, how they should position themselves in the world that is emerging for them, so that they can be productive and they can impact the future. So, we'll be talking many of these things. So, the first transistor was invented by John Bardeen, Walter Brittain, and Bill Shockley at Bell Laboratories at Murray Hill. And basically, what they did was to show that up till then, we used to have what's called vacuum tubes, which I don't think any of you have seen it. Uh, it was a very, very long old artifact which used tungsten filament to heat the electrons and all the good stuff. It worked, but it's clunky and big and all this stuff. And they showed that they could replace a big clunky gas filled or a vacuum and a you know, biggest or a very very slow triode, not a diode but a triode, with a solid state, easy to manufacture, easy to put it together and run, and better, faster, and much more power efficient thing. Then they could do that. And AT&T was very big in telecommunications, telephony, and they needed switching systems. They moved from electromechanical to electronics many years ago, electromechanical rather. And this transistor allowed them to miniaturize it further. So much so that this was a landmark change in the way the technology is being applied for building switching systems. And since AT&T had deep pockets and the switching system is a mainstay for it, for the entire operations, they were able to fund it. And then very quickly, from 1947 on, lot of efforts made into making this operational. So between 48 to 61, 60, 65, somewhere in that ballpark, lot of new activities took place. Very, very aggressive, very effective. Some of them in the electrical characteristics and configuration and how to make transistors from one transistor into a network, into making the various functions, operational amplifiers, and all the other stuff. And that's another movement towards how to manufacture this cheaper, better, faster, with what kind of a technologies, how can we use different materials. Original one used germanium, and later on, how do you do silicon, and how to grow the silicon crystals and all these things. So there were advances in both mechanical, in materials, and in electronics simultaneously happening through the course of these 20 some years. So here is some of the milestones in the early history of transistors that allowed us from a transistor, a proof of the effect or proof of the transistor effect, to making it component part of it that can be included in the circuit boards and which can replace, for example, relays, and essentially be replaced and brought into the telephony network. So early transistors were pretty, even though by today's standards, they were pretty big, but relative to the standards of that time, it is much miniaturized. So here is a picture. This coin is approximately 2 centimeter diameter. And so you can see how a single transistor, you can buy it. Even today, you can buy single transistors if you want. And these transistors are embedded and they can, very much well packaged, so that it functions basically with a emitter, collector, and a base. And you can connect them in various kind of circuitry and do all sorts of interesting things. From one transistor in 1959, we started moving towards using it in the actual use. And at that point, we said, why not, if I'm going to take two transistors to connect, why not I connect it in the circuit itself, in the transistor itself, cascading one to another, and two to four, and two to three, and all these things. You can cascade one by one and interconnect them in the chip itself, so that you can now realize complicated circuits right on one chip instead of taking individual transistors and putting them together. And this led to multiple things. For example, 1960, your one transistor, one gate, NAND gate or NOR gate can be done with one transistor. The circuits have been slowly and steadily being designed for that kind of thing. And then your multifunction, to the medium scale integration, and to the very large scale integration. Now, when we call very large integration, that's approximately 2,000 to 20,000 or so, approximately, give or take a few, so many of the transistors in a particular chip. Even though for them it is very large, today it is absolutely nothing. 20,000 transistors is a child's play. Because they are small, because they are compact, and they are interconnected at the chip level, it takes less volume, less area, and consequently less power consumption. It's higher speed because you don't have the delay in translation between the circuit signals going from one place to another, because the distances are very small. So you can make it faster processing and very high significant cost savings. That was the incentive for this to come on board into the real world. So through the course of history from there, from the start, we noticed that we started with two branches. One is using the microprocessors as a memory, and another one is using the silicons as memory, and then semiconductors as logic chips, which is where the computing CPU, the ALU, and all the other things that you put in there. So there was sort of a branch off at that point, but they're operating in parallel. One technology gets into another, and they're sort of interchangeable, learning from each other. But when you're doing semiconductors for memory, the implementation is much simpler compared to logic, which is a lot more work needed to be done. And nevertheless, Intel, which is one of the biggest players at that time, and even today, what they noticed is that the number of transistors on a microchip doubles every year. That is the march of the technology. When you build one technology, you build on top of the other previous technologies, and then you follow with another advancement. And this advancement was happening all around the place, all over the world. And these advances led to looking at this thing, saying we are able to put every year or every 2 years, we are able to put double the number of transistors. That means double the functions and double the capabilities and half the price. So with a lower price, we are putting more transistors. So per transistor price is becoming lesser and less. So Mr. Moore, who is the president or the co-founder of Intel, made this observation, and which sort of took a kind of a law, expectation of what will happen, even though there is no physical reason why the law should be there. There is no such thing. It is just a statement of the fact of life, that every number of transistors will be double, and correspondingly the cost will be halved. And that went on for several years. Initially, it was an observation for a period of few years, and then we saw that it's happening again and again for a long period of time. So we are making the distance between the transistor, each distance between two transistors smaller and smaller and smaller, because of the same space you have to put double, you have to reduce it by factor of 2, the distance. So we're doing that. And it's been going on for a while and still continues. Every time we thought, oh, that's it, we reached the limit. Somebody comes along and said, no, they were able to break that and make this happen again. So the idea, why is this important? It is like a self-fulfilling prophecy. When people are doing in the business and in the market and the technology and the consumers and everybody, there is an expectation built in and what's going to come next, because everybody wants to get the latest and greatest. So you're expecting what is going to happen next year. And this law, certain quote, gives you an understanding of the expectation of what's going to happen year or next year or year after that. So what is coming upstream, so that that expectation drives the innovation and the research and moving forward. And we're seeing that happen because that is almost an expectation that is real because we wanted to make it a real. So Intel, for example, had gone through this cycle for many, many years. We started with, in this case, 90 nanometer difference between the two transistors. So the interconnect region apart is about 90 nanometers. That's called a line width. And this continuously got smaller and smaller and smaller with better equipment, more efficient processing, different technologies. All this brought from 90 to 65 to 45 to 32 to 22 nanometers and so on. And we are now in the range between 1 to 5 nanometers range. Now, just for the measure, 1 nanometer is approximately 6 to 8 atoms. So as we are coming in to the angstrom range, basically, we are really crossing the border between multi atoms to a single or 1 or 2 atom range to do the thing. So we're really crossing a border between macro level to an atomic level transition. And that has large implications. So there is always a thought that when you cross that border, you're going to have some real transition pain. And so, how long can this Moore's law hold is a conjecture because it's not a physical law. But we have been able to, so far, all the way we are coming to about 5 nanometers, 3 nanometers, we are able to handle it, and we are able to show that we are able to put more and more chips at half the cost, and better performance and everything else. Now, why this is very important for us to think. Why is it in India's innovation? Why it is relevant? Where exactly in this evolution do we want to join is something that you want to keep in mind. I will come back and talk about this when we'll talk about the Atmanirbhar and all that stuff. But as this evolution going on worldwide, different countries started joining at different points, from first Japan, then Taiwan, and finally China, and hopefully India in the future. So in the case of memory, for example, the world is creating approximately 270,000 petabytes. Now you talk about megabytes, gigabytes, terabytes, and now you're talking petabytes. So it's about 27 into 10 to the power 19 bytes of data every single day is being generated. Now you might wonder why, where is the data coming from? Where is it generating? We are generating in biology. We are generating in bioinformatics, DNA measurements, things like that. We are creating this kind of a number of data in astronomy. Every piece of the world, every piece of the sky is being scanned every night or every day at different wavelengths. Every micro inch or micromillimeter of that area is being captured. We are having antennas that are recording the signals from all around the world all the time. So we are collecting huge amounts of data in astronomy. In financial systems, financial markets, we are collecting volumes and volumes of data. So we are collecting on average approximately, let's say 27, give or take a few, gigabytes or terabytes, in 10 to the power 19 of the data every day. By the end of this decade, we project that each of us will have 1 petaflop computing power accessible in the cloud. So using your little mobile, you should be able to connect to a server which can do at 1 petaflop operations per second, and 1 petabyte of data which you can access in less than 1 millisecond away. So these are all mind-blowing numbers. This is the expectation, and because the integration of that, even your phone that you have, I don't know how many of you realize, the little phone that you have has more power, computing power, more intelligence, more memory than the machine that went from Earth to the moon. The moon lander, I was operating, the entire power of moon lander is 40-watt light bulb. That's all the power they had. And the computation was very, very rudimentary, and we were able to go to the moon. But with the smartphone, we haven't even crossed the ground. gravitational field, even though we have some very good spectacular successes in the past. So, so the idea is that we always think that we have reached the limit of the Moore's law, and every time the world has surprised us that no, we still have a long way to go. We'll talk about more about this as we go forward. Now, this is a little bit of history. The Moore's law is guiding us, our process going forward. So let me talk about what is semiconductor processing for some of you, particularly mechanical engineering students who are there, or materials people who are there, how these things come about. And basically, it all starts with sand, purified, which is silicon dioxide, and that is converted to pure silica, and it is turned into crystals at a particular like different distances between atoms based on how it is cut or how it is grown. So you can get a long, big cylindrical pieces of crystal, silicon crystal, crystallized silicon. Typically, these bars are about 30 centimeters, the size of a decent plate that you have at home. And this is taken and sliced into multiple pieces. So take each of them and slice it with very thin using lasers, and then you polish it. Now you have a clean 30 centimeter diameter silicon with all of them are silicon atoms uniformly located. You start that wafer and then you start polishing it, and you take the circuit that you want to design, take a picture of that, and use that with a laser etching model with a photoresist. So you put a photoresist similar to what you do in a photography. You have a coating on the silicon, and then you shine light wherever you want, depending on where the interconnection lines are, where things are, and then you melt that photoresist, and then you apply dopants, and then you keep building on this one piece at a time. So today's chips can have maybe 20, 30 layers of it continuously. So once it's all is built, so you have in a silicon one wafer, you can have literally thousands of little photographs, all identical, etched. You take that and you slice it into small individual chips, and then you put them in a container in a place where you connect all the wires to outside, and you package it. And there are many ways to do that, and there are many kind of form factors. We'll talk about that, and eventually you get what's called a chip. So from the beginning, from wafer to this, is a very interesting evolution. It requires a lot of things, and some of the things that we want to talk about are here, which are some unique challenges. Today's semiconductor processing, these are some of the challenges. From the wafer manufacturing to the etching process to the packaging, first thing you need is a lot of water. A fab for making semiconductors needs a lot of water, approximately 2 to 4 million gallons per day on average. And some of the water has to be purified to the nth degree, called deionized water. You use almost 500 or so very toxic, hazardous chemicals, highly corrosive chemicals are being used in this process. It has, its typical fabrication has about 500 process steps, each very complicated and involving very highly complicated and expensive equipment. And it uses power. A typical fab can use up to 100 megawatt hours of uninterrupted power each and every hour. So you cannot not only need a large amount of power, but this power cannot be interrupted even for 1 second. So you see the conditions are necessary to make this happen, and how we have in the world we have done this so far to make this kind of things happen, to make this kind of chips, is an amazing engineering activity. This hopefully will make sense to not just electrical engineers, but to mechanical engineers, to civil engineers, to to material scientists, to chemical engineers, how you are going to be able to provide this kind of environment for somebody to build a semiconductor fab. So this is what's being done, and that's what drives the cost of a fab. We'll talk about this again in a few minutes. So, particularly from the chemicals point of view, many of the chemicals used are hazardous, but we don't know many of them because it's not even recorded, because the chemicals are hidden behind trade names or combinations of it into branding. So we really do not know how sensitive, what's the long-term effect of this. So we really need to be careful about when we are using these chemicals, how we are going to use it, what kind of protection for the people, both in the factory, outside, are going to be covered. And these are all the major issues that we will have to grapple with when we are talking about semiconductor processing. Why are we talking about all these challenges? These are the places where innovation needs to happen. And we'll come back to that topic again when you're working as a student, as you're learning and doing things and going forward in the semiconductor field. Where is going to be your world? What kind of problems that you're going to face, where we come, and how are you going to change it to make this world a better place? The packaging, which we talked a little bit at a time before, basically there are many types of packages. Typical packages are what you see on the extreme left, a typical computer memory chip, or you can get a CPU chip that you can buy. But the chips also have other forms. Your credit card, for example, your SIM card, all of them also are semiconductor packaging chips models. And everything built in, something visible, something not visible, the Wi-Fi, your routers, everything, your computer, all of them have various forms of chips, not only chips themselves, but the shapes and sign, everything is different. So we are reaching from a traditional packaging area to an advanced packaging area where the smaller the chips, as the chips are becoming smaller, you have to put it and you have to make the electrical contacts and you have to make them function in different formats, sometimes with power, sometimes without the power. Sometimes the Wi-Fi is providing the power, so you need an antenna there. So many other things need to be integrated, and we are entering into an advanced packaging era. Along with the technology development in the fab, there's also movement towards packaging and testing era that's changing. And so in the packaging, even Gordon of Intel said it may prove to be more economical to build large systems out of smaller functions which are separately packaged and interconnected. This comes with the understanding that maybe Moore's law would run out at some point, that we can only put so many transistors, and if you want to build bigger systems, you might have to combine them and put the combination functions in the integration rather than in the actual building chips. But we haven't reached that yet. In fact, it's the opposite. We're creating more and more complex chips on the fab, and we need better form factors, different form factors that makes it usable, for example, in a smartphone or whatever it is. So we are still in the era of able to miniaturize it, able to put it into different form factors and make it usable in different kind of environments. So far, we looked at the history. We looked at where we have been, with some glimpses about what is going to happen in the future. So now, with that as a background for those of you, hopefully it will be useful to keep in mind. There is a lot more to it. I'm going to sort of quickly, cross the boundary. And we are going to talk about innovation opportunities in semiconductors for those people who want to be doing things in the future. Again, semiconductors does not always mean you are an electrical engineer, even though there is electrical engineering. It's a big part of that. Not computer software, because your computer software is also a part of this, because computer software and hardware are very commonly integrated in the context. Every hardware has a software needed, and software depends on the hardware. But we are also looking at the future in the timeline. What is going to happen in the future? And essentially, there are three areas that you would probably want to look at. The essential technologies refers to what is today. You got the idea of how we got here today. We saw some of the challenges that is not yet solved, but it makes it work. We can deliver things, but along the way we had some real hard difficulties that we had overcome. It's not the most optimal, but that's the way technology evolved. So what are the technologies basis that is foundations for us to do it, and how can we do that better? How can we do that more efficiently, more sustainably? And there are a lot of innovation needed for that. There's new capabilities with the existing products, with the technology you already have, and the evolution that is going to go on along with the Moore's law trajectory. What more can you do with that? Where else can be used? The same technologies can be used. I mean, same technologies that had we allowed it for going to same smartphones, for example, or Wi-Fi, for example. So the advances in the capabilities and the advances in the technologies go hand in hand. Because you have a new form factor, then your technologies start developing to meet that need. So how do we make sure that we are able to build this better? How are we going to extend that into the real world today? And what is coming on board completely different, what changes the models, what is going to happen in the innovation, where the research is happening, where we are going to see a paradigm shift from what we are doing. All three areas are exciting areas to think about from an innovation point of view, and there is a lot of places where young students can get involved and work to make the world different from what it is. So in the essential technologies, I picked about three areas that are relevant. Again, without going into the very specific items in innovation, I want to give you a bird's eye view for all of you guys to think about. And I'm sure that each one of the persons interested in this kind of activity would pick a favorite topic that they think is valuable and work on it. There's so many areas, opportunities there for young people to get in and actually do better than what we have done in the past. Process improvements. We talked about semiconductor processing as over 500 steps, and each step is complex and it involves complex equipment, etc., etc. A process improvement. There's so many places where you can intervene in the process and make it change to the point that it is more efficient, better use of the power and the water and stuff like that. So your process improvements is a significant area of innovation available for semiconductor processing. Sustainability, again, that's one of the reasons I mentioned to you about the need for water and need of use of all complex chemicals and of electricity is how do you build, if semiconductors is considered new oil, it is fundamental to our survival of the human race at this point. We have become so dependent on semiconductors. But if you want to build those things, you cannot build the old way with all the complex chemicals and polluting the environment. You cannot do it. So you need new ways of doing and using these chemicals safely, making them, using them, disposing them off. And so sustainability is going to become a big issue. And we need people to think about how they can do it. Maybe alternate chemicals instead of the chemicals that are used. Maybe use some other chemicals, or maybe use different models of manufacturing. Supply chain enhancements. The COVID-19 has brought together a fact that there is a huge interdependency between countries, and the COVID disruption with the geopolitics associated with that have shown that we have a supply chain is very fragile, and today it is completely broken, in fact, to the point that we are really the society is hurting itself, self-inflicted damage. So how do we create a better supply chain model? How do we build a collaboration within countries and within all the players so that things can happen smoothly to make the research and the innovation continue? So given the current situation, what we there, if somebody wants to go look at it and say, there are areas I want to improve and do it, there are some areas that I'm pointing it out to. And there are a lot of people will be talking. We'll be talking in expertise semiconductors as well. Many of the things we discuss, and we'll be happy to engage with many of you. The second is new capabilities. When you talk about what you have and where it's going to go, semiconductors has become a new oil that is pervasive, that is involves and has a role to play in every part of our activity, professional, personal, whatever it is. So there are a lot of new applications where applications and devices need to be built. Whether you're talking about transportation, for example, electric vehicles. The electric vehicle space is said that electric vehicle is nothing but a computer on wheels. There's so much of almost every part of that is a semiconductor. Chips have a role to play in electric vehicles. So much so that today, because of the limitations of semiconductor availability, automobile companies have stopped their assembly line. Ford and General Motors and all of them have, they cannot completely finish the cars because some critical semiconductor components are not available to them. So they cannot make it, so they cannot sell it. So but literally it blocks them from moving forward. That amount of dependency of the automobile EV manufacture, sale and use is dependent on semiconductors. We see that happening now. Energy is another field, perennial favorite, with the semiconductors being a part of it for generation, storage, transmission, and use. Everything is and measurements. All these things are semiconductors have a role to play at each point. In healthcare, medical devices, and other applications, tools, everything has semiconductor. Communications, telecommunications, of talking to each other, your smartphone, everything is involved in semiconductors. Food and agriculture, space and defense. So there are many, many sectors. I mean, I can go on list everything. There are only two areas where semiconductor. I used to joke that there are two areas where semiconductors haven't become a major issue, or AI is not become a major issue. That is, one is religion and another is politics. And I hope semiconductor goes and makes the change also there, so that we can get more sanity than what we have in those two areas. In any case, new solutions, robotics, drones, IoT devices, sensors, education technologies, and financial technologies, all of them will have a bearing on availability of the semiconductors, the memory, the access to the servers and cloud computing, and all these things will influence in the future new applications, new ways of doing things. And I hope that many of you will be involved in developing these new solutions and new innovations in this. New markets, we talked about supply chain, global markets where the interdependency of the countries are a direct important part of it that we have to understand. We have to help each other out. All the countries have to work together to make sure that we are able to move forward with the technology like the way we have done in the past as a collaborative model. Moving forward, new concepts where you're thinking still further out, maybe 10 years from now, 15 years, whatever, or maybe is more recent than that. What is going on? For example, new solutions. If we can extend Moore's law applicability in the future, we are coming to a situation where we are crossing the chasm between multi-atom to a single atom. And that has some unique characteristics, unique implications. The extending Moore's law in the new regime is something of a challenge, and we need to address, and there's a lot of innovation needed in that. Advanced materials, energy storage and energy generation is very important. One of the biggest problem is energy storage, the battery technology. And what kind of a new materials other than the standard lithium? Lithium is proven to be a very good but very, very hazardous material, and it is not the right way yet proven itself safer to use yet. So we need to get new materials, new methods of storing energy and sharing and distributing the energy. Big data, as you say, like humongous amount of data is going to be collected and processed. How do you make sense out of it? Where is the computing going to come from for supporting that? These are all requires not the traditional way of looking at. but completely different way. You have to think outside the box. Say, how am I going to solve the problem? Because traditional ways of doing the solution have come to a bottleneck. We come to a dead end on that. We know the problems, but we don't know what the solution is. And we need people to think new ways of doing it. New technologies, as I said, we are going through the quantum, we are going to a single atom level. So quantum tunneling, quantum computing is a very important part of this kind of thinking. Artificial intelligence and machine learning, I can have talk about a lot more. You guys know it, same as nanotechnology. These are all up and coming areas which has very, very important implication of how world is going to change. And for the students, I can include biology in there. Biocomputing, for example, is one more area where we are going to understand from nature, from human body, how we analyze, how we do heuristic programming. All these things are newer technologies. It's a complete shift from the previous ones. And we need people to think along those lines for the future. New world, space applications, new medicine and cures, sustainable solution, and how do you address societal issues like global warming and climate change issues. How can the computation, how can the semiconductors be a player in that and solve the problem? So these are many of the things that are issues there. I hope that in a very short time, I gave you, touched upon many of these things so that some of it might be of interest to you and pursue that dream. Dr. Abdul Kalam has talked about dream, and what is here is all the places where you can dream and you can make a change. And so pick one. If you can do one tiny piece of one part of this, you're making a change in the world, whether it is improving what we are doing now or creating a brand new world. There's opportunities are endless. Atmanirbhar Bharat is our initiative in India. So we change the focus from the global to India. And if you're talking about the model of how to make India self-sufficient, so we have to develop technologies that make India self-sufficient. That's our goal. And from an innovation point of view, you're not going to become innovative by saying we are innovative, we are innovative. Just saying it doesn't make it so. You have to work at it. You have to work very hard at it. The You have to dream plus hard work is the only one that's going to get us wherever we are. So while we are celebrating our successes in innovation, we also have to teach our youngsters that that path to innovation happens with hard work. My role model, my one of the thing person I really love about it is Miss Mary Curie. You read her biography and you'll see what hard work means, or how a scientist dedicated to that does the work to get things done. Her biography is something that every student should learn and hear, understand. Coming back to the India model, there are multiple things we can do. We need to develop an R&D way of thinking, and we have to build infrastructure to support the R&D. We are going to, in expertise semiconductors, we are trying to build semiconductor fabs. So as others, we want to promote indigenous R&D in semiconductors and biology and bioinformatics and everything else. And we are trying to work with other countries and other people to facilitate the tech transfer and collaboration into India, so that Indian students can work with the world-class technologies and move forward instead of repeating and reinventing the wheel. Our goal, as India, we need to develop trained workforce, a meaningful training, not the one that wrote memory doesn't work anymore. You have to understand what you're learning and apply it properly and learn from it. Experience counts. Create good career opportunities so that students will come to STEM programs, STEM areas, and learn about it, learn and do. Mathematics is the core of it. People should learn more, get into more in mathematics and statistics and areas like that. That's very, very important. Collaborative learning. Indians are good. We are very, very good. We have proven that world over. But one thing Indians are not good is how to work with each other. We know how to work against cross purpose, against each other in cross purposes. We know how to compete with each other. But can we work together to make it happen? in the world, 1 + 1 is 2.5. India, 1 + 1 is 1.5. We keep tripping each other up. So we have to learn how to collaboratively work, support each other. I mean, I'm very maybe harsh in that because there are a lot of places where Indians know how to work together. But my experience, to some extent, is I wish we can do more of the collaborative work, and we have to create the incentives to learn and grow. Encourage innovation, incubation model, mentoring and coaching, and telling what is the right way to be an innovator and entrepreneur. And we have to provide meaningful, appropriate, adequate support and encouragement for youngsters so that those people who are motivated to be innovative don't give up, don't feel distressed or discouraged. So a lot of things need to happen in India for us to create a situation of innovation, R&D, focus, and growth. So we are trying to do many of these things. So I'm going to move towards what we are doing in expertise. Let me take about 5-10 minutes to share what I'm talking about and give some parting advice to the young students. Expertise itself is a broadly placed three components there. There is a non-profit section associated dimension to it. There is a for-profit dimension to it, and there is a hybrid, which is quasi non-profit, quasi for-profit environment. With reason. So non-profit, we have expertise research where we bring the youngsters from tier 2, tier 3 colleges, particularly. We want to expose them to the world class, the global population. We give them the opportunity to learn subjects that they will not only be dependent on what the local knowledge, but they can open up their eyes in the world over. So they can interact with the world over, many people, all the colleges, so that they can get better understanding of what's happening in the world and they can find their place in that. Our areas are biotech and bioinformatics because for a variety of reasons, biotech is exploding in its capability and its implications. Biology in the last bioinformatics 2 years ago, 3 years ago is different from bioinformatics today. It's going to be different 2 years from now. Just as semiconductors have gone through this tremendous amount of change, bioinformatics, biotechnology is going through that right now. So another 2 years, people who are trained here are going to see a different world in biology and bioinformatics and biotechnology by using biology and other areas combined. AI, machine learning, artificial intelligence, data science is another area that is changing as we see it. There is, even though there's a lot of gestation period, long gestation period, but I am seeing that is breaking out and is doing new things, and we are trying to help them out, help the students to get the benefit of training, connections, and relationships and communications in that. Drugs and medical devices, we saw in COVID-19 situation, it took us less than 1 year to actually develop a vaccine. Previously, vaccine development was a 10-year exercise. So there is a lot of innovation going on like that, and we have created programs like Circle of Excellence, which is for promoting the high school students to start building connections with the rest of the world. And there are other programs, other initiatives in expertise, nonprofit. On the for-profit side, we have expertise semiconductors, which our goal is to be a player in the emerging semiconductor manufacturing ecosystem in India. And we are planning to build a fab, a ATMP, which is a test and marking and packaging facility. And we are trying to do that within the context of an R&D and the collaborations with various universities in India and elsewhere. And we're building a viable supply chain ecosystem. The incubator, which is the one that I am talking about here specifically, is our partnership with universities. It complements what the universities are doing, but it's bringing a virtual and a global perspective to it. And we'll be providing mentoring and coaching activities to support all the students and all the groups in our program. And we have a new framework. We are trying to create a new framework for motivating and mentoring students. We help them build a team with a diversity of skills and capabilities across the world. Everybody coming together to help each other and learn. We train them with ideation, brainstorming sessions, and we teach them how to develop a business plan and how to assess the market and how do you take an idea into market commercialization. We mentor and coach them. We work with them to actively to see what they can do. Can they build a team properly? How to help them develop a working team, not individuals but collective group. We try to provide them support to nurture them with meaningful support and resources to make them into world-class companies. And we have three, broadly speaking, three programs in Expertise Incubator. We have what's called a startup engine, which is designed for students and others interested in startups to begin their journey as entrepreneurs. Entrepreneurship is, there are many ways to interpret entrepreneurship, but entrepreneurship is a state of mind, is a state of being, how we do it. And in order to do that, we have to learn how to think like an entrepreneur. And we help them develop it because me included, many of us have gone through this trial by fire. So we know what to do, what not to do, when to give up, when not to give up, who to talk to and who not to waste our time with. We provide all that information, share them and guide them. An accelerator is for the entrepreneurs who already know how to do it to actually commit to a streamlined program and doing that to build their startups. And for Go Global program was for those people who have already done that in India now to build a world-class company. If you look at it, we are very good in computer programming, but we don't have a Microsoft. We are very good in, there are so many people who can do semiconductor design. We don't even have a fab in India. So if you look at Indian perspective, there is a lot more barriers to changing the mindset from what we are doing to what we should be doing, and we are trying to be a player in all these things. So my parting message to the students or young students are, when I was a young boy many years ago, that I was told, when you go to school, you study well, you get good grades, and when you get a grades and you can get a job, and you'll get good pay, and you get a home, marriage, blah, everything, all the things that entail that, and you'll be retired and you'll be happy. That's what the trajectory was given to us as a culture. It didn't happen to us. I mean, every point somebody said, if you do this, it will happen. I consistently noticed that wasn't happening because I am already in the transition situation. It may have happened 20 years ago before me. Maybe it would have worked, but that model didn't work for me. And definitely it's not working for today's children or young kids. Today, you have to think outside the box. Grades are good, but grades are not everything. Nobody honestly cares about your grades. Do you know what you got in your grade last year? You may not even remember it. And nobody else would remember, nobody else would care. What you did with what you learned is the key factor here, and how you work with people. Look around you, your person sitting next to you. These are the people who are going to be your colleagues and future people you're going to work with. Learn about them, learn how to work with each other, learn how to build on their strengths so that you can contribute and they can contribute, and 1+1 becomes 2.5 or more. You need to learn the right lessons. The old history model of getting the grades and getting a job and retiring is not there anymore the world over. If you want to compete in the world, you change with the world. This is one single message. We are creating expertise, we are creating programs, we are creating knowledge, and we are having this webinar and presentations and all these things because we want you to be innovative, but we want you to understand what innovation means, what entrepreneurship means, and how you can live a world better than what you inherit from us. So this is my thought process. Thank you very much for listening to my thoughts for the last, 30, 40 minutes. I'll be happy to answer any questions that you have. And let's see. Okay. I'll be happy to answer any of the questions and thoughts and share. And I hope this has been a little bit of useful retrospection for all of you. Thank you.
Natarajan sir, are you available, sir? Hello.
Hello.
Any questions from participants? If you have any questions, you can drop your questions in the chat box so that we can proceed. One minute, sir. I can try to contact with Natarajan, sir.
Okay.
Okay. Sir, am I audible?
Yes, you are.
Thank you, sir. So, on behalf of IIC, thank you very much, sir, Professor, for your wonderful presentation on startups and opportunities in semiconductors. So here we have the nearly 60 students are sitting. We are streamlining your lecture, sir. So some students are interested in asking the questions. So I will hand
Sure.
over the.
Sure.
Tell your name. Okay.
Good morning, sir.
Good morning.
I'm Soma Shiva, sir, from Mechanical B department, sir. My
Okay.
doubt is, could you explain me how nanotechnology plays a vital role to increase the efficiency of semiconductors, sir?
Sure. You're looking at the entire model, business model, the technological model is the Moore's law. When you're talking about line weights of 90 nanometers, 100 nanometers, or even more, or 200 nanometers sometimes, you're talking about processes that are happening in ad hoc state, okay, average or the ensemble averages. But the technology is moving towards the nanometer range. 5 nanometers, 7 nanometers is been proven, and there are devices that operate in that range. Now, nanotechnology also operates in the obviously in the nanometer range. But what does it mean by operating at nanometer range? The physics of interactions between atom at the atomic level or at the molecular level, when you're talking 5 nanometers, 10 nanometers area versus 100 nanometers, each element is surrounded by a certain amount of atoms or molecules or whatever, right? And the behavior is immediately changed by its immediate neighborhood. And that's what makes nanometer or nanotechnology so precisely definable, and the kind of functions that you can implement there is much different from when you're doing at a large ensemble average model. So here you have a convergence of the semiconductors operating at that level, as well as the nanotechnology, which is operating completely differently but coming to the same dimensions, physical dimensions, leading to the same physics, for example. So what will happen in that is there is a lot of places where this interaction takes place between the two technologies. A semiconductor processing technology, where you're operating solid state with doping, etc., and the nanotechnology, where you're looking at the physical processes and physical characteristics and the chemical characteristics that entail based on proximity of the molecules at the nanometer range. How you apply that and how you use it is differ. In the semiconductor, we are primarily interested in using that nanometer range for reducing the cost, reducing the power consumption, and creating a transistor effect. Essentially, transistors are nothing but valves. Think of your home, a water tap, as a transistor in a way, because all you do is you have an input water coming in, output water going out, and you have a valve that you can turn it off. Likewise, here, input and output, and then there's this electrical signal that controls it in a very, very rudimentary way. That is one way to do it. And now you're miniaturized to the point. So you're going to, but the nature doesn't care whether you're a semiconductor or whether you're something else. It operates according to the laws of physics. So you're going to see that these two overlap will lead to actually enrichment on both the areas. For example, biocomputing, can we build biologically inspired computers that can be used with better way of creating the transistor effects using biological molecules? Now, nature doesn't care whether it's a DNA or a semiconductor chip. Maybe if we can create that kind of model, then you have a different kind of solutions that emerge. The disruption of the technology into a newer model might happen. So there is, again, without going into the very specifics, and specifics have a lot of, there are a lot of seminars and a lot of universities are working on it. And so there is ample opportunities for you if you guys were interested to go and learn and think and bring. But I can tell you that all the people are doing, none of us know where the world is going to emerge and where the new idea is going to come from in the future. It may be coming from one of you guys. Okay, so we don't know. And best way to I would recommend is people go and apply themselves to learning the STEM, learn the foundation, and attend the meetings, attend the webinars. And there are so many opportunities that we are constantly creating so that this can facilitate you guys to come with the innovations that is needed to make the world a better place. I hope I answered your question in some way.
Yes, sir. So I have another doubt, sir.
Mhm. Go
In
ahead.
what aspect they are calculating the efficiency of a microprocessor? Like if we
What do you mean?
uh,
What do
take
you
Intel or Ryzen, which is best, sir?
I didn't understand. Go ahead and repeat. What is the two? What is it? Which is better? What are you talking about?
I think
Can you repeat?
I think Intel performance is much better than Ryzen, sir.
You it's a very simplistic question. Okay. Without defining the parameters, defining the context in which you are talking about comparing two things, you're going to run into the risk of doing apples to oranges comparison. Okay, so many of the things you have to understand, there is a technological results which are based on objective scientific qualified data, and then there is a market presence. Market say, this is better, that's better in what way? Everything has a place where it is more optimal. Okay, there is a role, there is a cost associated with that. We talked about transistors very early on, okay, where I said that transistor was a breakthrough because it replaced the tetrode, not a triode. Okay, triode is a vacuum tube, and it replaced that because for the switching applications, it's not a high current, it's a low current applications, and for that, triode is pretty good, and transistors replace that. But there are still applications today that requires vacuum tube where transistors cannot provide that kind of power output. There are power transistors. They are able to do that, but they're primarily used in the switching space. When you're talking about power in some really interesting military applications, vacuum tubes still excel. So, what is more efficient? What is more better? Depends on the context in which you're applying. What is your goal, and what is the technology, and what is it that you want to do based on the technology? And so, I don't think that there is any particularly simplistic way to say this is better than that without understanding the context of anything. This is generically across the board all the time. Sometimes you can make it, you can indicate that by and large saying smaller the chips will lose, reduce the power. But when you want to run high current, high voltage, then what do? It may not be the right tool because at 5 volts, if you fry the transistor, but you have to now run 50 volts, what do? You either have the front end, which is operating at high current or high voltage, or do something else. So don't go by the marketing and what you see in the literature per se. Good or bad is depends on the context. Or efficient or not efficient depends on the context. You as a scientist, you as an engineer should go behind the scenes behind the obvious and look at what is being discussed, look at the characteristic curves, look at the applications, look at the market need and the applications where it's actually going to be used and all the implications associated with that. And then you make a decision whether it's one way or the other. In fact, this is exactly what engineers do. If engineers, all that is reading the newspaper and giving something, then why do you need engineering degree? Engineers are needed precisely to declutter all these things and go behind the scenes and understand and give the right recommendation to their colleagues and to the decision makers. So learn the lesson, learn the basic things first, understand it thoroughly, because you need that in your career. The people depend on you for it. Go ahead.
Thank you, sir.
Sure.
Sir, I'm Dr. Natarajan, sir. So another student is waiting.
Okay.
Just another. Yes,
Sure.
your name? Yes, please go ahead.
Sir, I have a doubt, sir,
Mhm.
regarding the transistor, sir.
Mhm.
Sir, according to Moore's law, every
Mhm.
2 years the transistor gets
Mhm.
doubled, sir. But
Mhm.
at some time the chip gets saturated. Then how come the transistor being?
Mhm.
Sir, am I audible to you?
Yes, yeah, you are. Yes, you are audible. Go ahead. I can hear you.
Sir, according to Moore's law, the transistor are doubled every 2 years.
Mhm.
At some time the chip gets saturated. Then how come the transistor can be placed, sir, in the chip?
Correct. So you have your room. In the room, you have 20 people sitting there with 20 chairs. Each chair is apart, 2 feet apart. 20 people. Next hour, another 20 people come. You can accommodate the 20 people because you can put them closer to each other. And next year, another 20 people come. 40 people come. You can do that. You can keep on packing them closer and closer till a situation comes when everybody only have to stand on top of each other. At the point you get saturation. The interesting thing is we think that this saturation will happen in 1970s and in the 1980s and in 1990s and then 2000 and so on and so forth. Every time people said, oh, we have reached no more space, we are able to accommodate double the people again. You see, somewhere we found the space, okay, to put the transistors. When we couldn't do side by side, we put one on top of each other. Okay, we did all sorts of funny things, so to speak, to see how we can pack because there was a financial incentive to doing so. If I am running a company and I have a chip that is running at say 10,000 transistors per square millimeters, and if I say that's all I can do, that my competitor comes along and they say they can put 20,000 chips on that, the transistors on that. Oh no, by the way, it is about half the price. So what do I have a choice? I can go run or get out of business. So what do? I hire engineers and I put new technologies and say, can I put 30 or 40? Can I leapfrog my competition? Competition is a very good thing from a business point of view. Collaboration is the best thing for engineering and technology. So what's happening in the thing is you will see the very unusual kind of a dichotomy developing in American industry. So, so,
12
so what will happen is on the business end, companies will compete like hell, but the engineers from each of the companies will talk to each other in the meetings and share information freely. Because I know that my survival from a technology point depends on my competitors, companies coming and telling me what they're doing. So if I make a mistake, I tell them, so they won't make that mistake. They will try something else, and they make a mistake, I will know. So engineering is a healthy sharing of information, while the business guys compete with each other for market share. Such a thing should develop in India. There needs to be a collaboration spirit in engineers. Talk to people about science, about technology, and make this happen. Let the business guys worry about competing and making money and all those things. That's a part of it, important part of it. That's what entrepreneurship is. You have to do better than the other guy so that you can survive. But how many people can you put? Your ingenuity, your ability to put that is what that is important. Okay, how do you do that is a question, $1 million question. We are reaching the limits of it at the atomic level, at the physical level, but quantum computing can change the whole thing completely, because your information is no longer in a bits, but it's in qubits. A qubits gives you a multiple data points simultaneously. So instead of storing the information as 0 and 1, you are storing 10 pieces of information in the same bit. So quantum bits can completely change the way we talk about science. So maybe 10 years from now, all this will be a history. And people, your children might think, oh, dad is talking about nonsense. Now I have this quantum computer which does all these things, or something else that is beautiful. I think this is evolution.
Thank you, sir.
Thank you, Professor. Sir, we have more students. So with this, we'll wind up, sir.
Okay.
Yes, you may ask the question. Your name? Elaborate. Yes.
So good morning, sir. I'm Lavas
Good
from
morning.
Mechanical Second Year. Sir, if I want to start a startup, how semiconductor will help us, sir?
Semiconductor is just a tool or a resource. Okay. When you
Semiconductor
want
interest
to
areas, sir. How it help us, sir?
when you want to start up, I would say that this is what I'm negotiating with your company, your college, and other colleges. We are working together, and join us. Work with us in expertise semiconductors, and there are programs that will guide you. If semiconductors is a part of it, it's a part of it. That's what we do. If not, there are many other areas also. The innovation transcends semiconductors. Semiconductors is important. It's important for a national security and national growth in India and elsewhere. At the same time, so is other areas too, technologies too. So it's not a question of whether you want to be a startup in semiconductors, but you want to be a startup and learn the right lessons. And if semiconductors is the area that your startup goes, there is a way to solve the problem. There is a way to help you guys out. Yes, it's very hard to give it in 2 seconds an answer, but that's precisely why we have an expertise incubator and other incubators in the country, and as well as the universities to help you out. Okay.
Thank you, sir.
Sure.
Thank you, sir. So, wonderful presentations, and also interacted with many students, answer the queries also. So, on behalf of IIC SVC Chennai, Sri Venkateshwara College of Engineering, we thank you, sir, for the wonderful presentation on startup and opportunities in the semiconductors areas. Thank you. And through behalf of IIC, so we will keep in touch with you, sir, in future also. We have many innovative work and startups. We expect your help, sir, in future. So, so we will keep in touch with Praveen Kumar, sir, and we will have in future, we will do many activities, sir. Thank you, sir. Thank you very much.
Thank you very much. Goodbye, everybody. Thank you.
Thank you, sir. Good night.